Alright, moving on to lesson 3. So for this lesson, by the time we're done, you will have an understanding of pressure-based equilibrium constants. You'll be able to determine equilibrium values and concentrations when you're not explicitly given equilibrium concentrations. We're going to develop this new quantity called a reaction quotient, and they're going to tell us if systems, if they're at equilibrium and if they're not, which way they're reacting, and then use Le Chatelier's principle to figure out what happens when you actively disturb an equilibrium. Alright, so some of the examples that you'll be able to do by the time we're done with this is this long one that involves carbon tetrachloride and it's decomposing. So feast your eyes on that, but fret not. We'll work through it step by step. And then we'll do a couple of examples involving this PCl5, PCl3 system right here. So take a look at those. Those are our goals. Now first, we're going to do another straightforward equilibrium concentration. This will be the first example with ice tables. It's increasing the complexity just one notch. Okay, so now let's crank up the complexity one more notch. So take a second and read this problem. And just think about what's different from the examples we've done so far. And that is that you were not given any equilibrium concentrations. So not even the stoichiometry is going to help you. All you're given is equilibrium constant and the initial concentration of one of the one reactant. So how do we do that? Well, first, I highly recommend write down the reaction that you're talking about. So always look at the reaction. And so we're talking about the decomposition of phosphorus pentachloride into phosphorus trichloride and molecular chlorine. So we've got one reactant, PCl5, and it decomposes into PCl3 and Cl2, all gases here. And check for balance because we know that's important and we're good. It's 1 to 1 to 1. All right. The next thing I would recommend is keep track of your initial concentrations, your equilibrium concentrations and the changes, whatever you know. So here, and maybe you make a table. So let's look at the initial concentrations here. So you're told the initial concentration here is of PCl5 is 1 molar, and these are going to be molar concentrations. I'll just give you the brackets here. And the implicit statement here is that if you only have PCl5 to start with, that the initial concentrations of the PCl3 and the chlorine will be 0. Now, here's a trick. Whenever you are completely devoid of one or more components of an equilibrium, especially if they're both reactants, if they're all reactants or they're all products, you can always assume some progress, either forward or reverse, to make some quantity of those components, no matter how minuscule, but it will in the end not be 0. So you can expect changes, and maybe we put those in a column. It says C, but we don't know how much it's going to change by. But we can maybe at this point think symbolically. Now, from what I said, you can expect some PCl3 and Cl2 to form, which means you're going to lose, I lost my C there, you're going to lose some PCl5. and we'll just, however the concentration is going to drop by, we'll just say it's X. Now at this point, you can exploit the reaction stoichiometry, that if the concentration of PCl5 goes down by X molar, since they react 1 to 1, you can expect the concentration of PCl3 to go up by that same amount. And same thing goes for the Cl2, because in this case everything's reacting 1 to 1 to 1. And then we can also symbolically construct what the equilibrium concentrations are going to be. So here we're going to have 1 minus X molar of PCl5. We'll have X molar PCl3 and X molar of Cl2. And now you can see why this is called euphemistically an ice table, because you've got a column of equilibrium changes, initial concentrations, equilibrium concentrations, and equilibrium concentrations. This, I just now learned this after a couple decades, it's often called also a Rice table, because you can have, technically the top column here is the reaction, but I just like calling it ice. So there you go. And actually, we can solve this problem now. Now, you were also told the equilibrium constant was 0.0211. So how does this work? Well, so the equilibrium constant is going to be, expression is just the concentration of Cl2 divided by the concentration of PCl3, or times, and then divided by the concentration of the PCl5. Now, in our symbol speak, this is going to be x times x, or x squared, over 1 minus x. And this is equal to, numerically, the equilibrium constant, the 0.0211. And from here on in, the chemistry is done. It's just algebra. And let's see, this can be an exercise in algebra here. If we rearrange this, I'm going to start working down here now. That equation could be rearranged in the form of x squared equals 0.0211 minus 0.0211x and so here you can maybe see where this is going. This is the quadratic equation, and they are solvable. So what you want to do is, for a quadratic equation, rearrange it to the form where you've got everything equal to 0. So we just have to bring these terms over to the other side. So we're going to have x squared plus 0.0211x minus 0.0211 equals 0. And this is the form that you can actually solve. And I'll just do this up here in case you have forgotten this from algebra. The quadratic equation for an equation ax squared plus bx plus c equals 0. The values, or the roots for x, are equal to the quantity negative b plus or minus the square root of b squared minus 4ac all over the quantity 2a. And so in this case, I'm going to write the implicit 1 here. So a is 1. This is going to be b, and this is going to be c. Now, I will tell you that this is going to take some practice. I rarely work that into my calculator and get it right the first time. I just keep going until I get the same answer twice and then usually call it good. Let me give you an intermediate step here. So the quantity b squared minus 4ac in this case is equal to 0.291. And if I get 3 in there as an extra digit there to minimize the rounding error. And then the way that you do this is you run this calculation here twice. Once adding that square root quantity and then once subtracting that quantity. So you get 2 roots, which is what you expect for an answer here. And you get x equals, one of them is 0.135. And the other one is negative 0.156. Now, which one is it? So it will always be the case that when you do this, if you have done the quadratic equation correctly, one of the roots will make sense and the other one will not. And here's what I mean. That in this case, this negative 0.156 root, that would give us a negative concentration for PCl3 and for Cl2, and that doesn't make a whole lot of sense. So we can discount this root and then double check to make sure the other one does in fact make sense. And so that gives us positive concentrations of these two, which is good, and this one will still be constant as well. Now, it is often the case that the negative root, if there is one, is the one that doesn't make sense, but not always. So don't count on that being the case. Go through and check both of them. And so all that remains now is to actually, the question was what are the final concentrations? So we know that these are going to be 0.135 molar. And this one clocked in at about 0.856 molar. And I would say always double check to make sure, and this is a good way to catch for math errors, make sure that these concentrations that you have actually do give you the right equilibrium constant. So I've got 0.135 squared divided by 0.856, and that does in fact give you 0.0211. So yay, we're done. So this basically is how you do an ice table problem. Generally, you're only given initial concentrations. You have to, using the stoichiometry, symbolically figure out what the changes are going to be, what the equilibrium concentration is going to be, and then it's algebra from there. They're not going to get a whole lot more complicated than this one. So if you can follow through this one and ones like it, you'll be fine.